set up. All right. So what we're going to do is we're going to make sure under add-ins, when you go to look at Circuitworks, you want to click to enable it. It will be available to install from your set of extensions based on the license parameters. Circuitworks can be a little bit clunky. So there is a tutorial that you guys are going to be walking through. So again, that's going to be home under learn. The step-by-step tutorials. You're going to go here and you're going to go to productivity tools. There are some for simulation, but there's also for simulation. Circuitworks Basics. So this is the one that you guys are going to be going through. There's going to be a couple questions about this, I'm sure. So let me see if this file is in the normal location, which it should be. So it should be under users, public, documents, SolidWorks, samples, tutorials, Circuitworks, examples, and you're looking for the IDF3 format and cell phone. So this is going to walk you through this tutorial. This is what the file looks like, and what you're looking for is they've got a couple different file types. So there's an ENM and an EMP. Basically, what you're looking for is you're looking for this particular CAD file. So I'm going to open this one. I think is the cell phone. So I'm going to open the ENM file, and this is I'm actually going to go from here to open, because if you're trying to open it through the normal Explorer, stuff happens and it will be very confusing. So go here instead. So through users, public, documents, SolidWorks, 23, samples, tutorial, Circuitworks, examples, IDF3, and then cell phone. There's a couple steps in there. The add-ons tab, SolidWorks add-ins, should already be enabled in your command ribbon up at the top. So I don't want you to ever show this again. Build the thing. So there's two different files. I want you guys to see examples of what those look like. Because there's a couple examples. Another reason why I want you guys to be able to get started on this is these files, when you're doing Circuitworks, take an inordinately long time to process. So even running along at a stable like 4.6 gigahertz or so, it's just not a multi-threaded application, and so it is what it is. If you're one of those fortunate enough to be running 6 gigahertz or nearly 6 gigahertz because you're running on liquid nitrogen, great. If you're using a regular person computer, these files take a long time to build. So you'll want to open them and let them start running and compiling in the back end, because that creates lots of issues. So yeah, you should have under the add-ins Circuitworks available. If you don't have the add-in, like you should have the add-ins ribbon available in the command window. If for some reason you don't have that displaying, you come back here to View, Workspace, no, Toolbars, and make sure that your command manager is enabled so that those tools are available. This takes an awful long time to build, but you can see it does walk you through. You have to have SolidWorks. You have to have it enabled. And so you can also get there from Tools and then Add-ins from the menu. So up here, Tools, and then Add-ins, which is down here. So you click Add-ins. So there's a couple more things at the bottom there. Tools and Add-ins, Circuitworks, and then click OK to enable. So then it'll tell you about opening a file. So then once you've got that, you're looking for a couple different things. There's a couple different kinds of components that you're going to be drawing. The actual drawing files themselves are so there are a couple that you haven't seen yet. 2-pin headers are a thing, definitely. Grab this real quick. Two-pin header. Another one we're going to need, for instance, is a 3-pin header. So you're going to draw each of these components. You're going to draw the 4-wheel drive control board as a whole. You're going to draw an LED. So this is part of how to draw from a spec sheet. So many times on a spec sheet, there are physical parameters. So this is the type that you're using. They also give you some dimensions about reels and things. Those aren't particularly helpful for right now. We're just focused on the actual architecture itself. So it looks on this particular image almost like they're shifted a little bit, but it's actually just a ridge all the way around that LED. And a resistor from a spec sheet. So they give you some different types, but they give you kind of the general functional geometry. So some of those height parameters are given here based on the sizes. And so for most things that you're going to be doing, you're on the order of like an 1/8 watt, maybe even these might be 1/4 watt. I think those are reasonably common. 1/4 watt dimensions. So H and L and D, so total length, diameter. Those are things that you're going to need to know, because what we're actually designing and drawing now, we're going to be doing this tutorial in Circuitworks, which is Just the most amazing piece of software ever devised by man. You're going to be changing some parameters. You're going to be creating an entire circuit from these components. You're going to put together the control board and the circuit. The reason being, one of the next big projects that we have going on actually is this. So you're going to be recreating four-wheel drive cars for the big race at the end of the semester. So these are composed of some kind of a body that goes on a chassis. I picked this particular one for a design philosophy I wanted to try in one of the last ones that I ran, to see if I could make it work. The results were a little bit underwhelming because the spec sheet, we'll talk about some of the actual components themselves. The spec sheet is a little deceptive in terms of what these motors can and can't do. They are good little motors. The problem is you have to create, and you'll actually be able to see this a little bit. I'll see if I can get it to refocus a little bit. There we go. You actually have a circuit that you're going to be working with. It's going to look something like this. So it has a small resistor. There we go. Has a small resistor, has a 2-pin header at the top there, and a 3-pin header at the right side. So stage left for me, but that's okay. Has an LED to indicate power, so that when you hook up power to it, you'll get a light that comes on. So just like that. So switch, light comes on, light goes off. You're going to be creating the battery pack. You're going to be creating basically all of these parts. You're going to be creating them in SolidWorks so that you can recreate the entire chassis. You want to make sure that when you build it, you have the switch actually physically accessible. So mine sat in place up at the top. So you're going to want to be able to have some kind of an access hole planned. I had some space constraints and packaging related issues, but this way I can bring connectors out the side, hook them up, and then easily have access to the switch to be able to run it, because you want to be able to turn it on and off. You don't just want this running and draining the batteries completely. So you're going to be recreating the circuit, and they want you to do that in SolidWorks. SolidWorks is not super great, so you're going to be building an actual physical assembly, like a normal assembly, rather than trying to do it in SolidWorks quite the way that they intended, because that just does not work in a way that makes sense. You're going to be creating a copy of the motor. You're going to be creating the gears themselves. So this particular one is a one-sided drive motor, which means one gear up here. Most of the motors you have are going to have two-sided drive, so gear on either side. You're also going to have four-wheel drive. So this one, I don't recommend this particular arrangement. It might work with the smaller drive gear. I went for the very rare, at least at GCU, very rare and elusive pink gear, because I wanted this particular car to have the opportunity for a maximum top speed. So this is capable of exceedingly high RPM. I'm also using an illegal motor for this particular build because I wanted to try and go for absolute max RPM, all out top end. The problem with that is these motors have virtually no torque whatsoever, so they don't have enough torque to overcome the basic rolling friction to keep them moving. But you can see when I turn one tire, all four rotate at the same speed exactly. So that keeps things very, very easy. There is a little bit of gear lash, which means if I hold the tire steady, it wants to move. And the more gears that you have, the more gear lash there is to take into account. So there's a little bit of play and rotation there. So in this case, it's across all of those gears, almost an eighth of a turn. And you'll want to recreate the battery box. You're going to get one just like this. So there's a couple components that you're going to get some measurements off of. I managed to get most of the components set up, but we're going to talk a lot about chassis setup, dynamics, strategy, gearing, how to put together the body, all of those things. I need to put together the teams so that those are all put into place. There's a lot of things that you guys are going to want to take advantage of. So yes, there is going to be recording from today. As far as opening the SolidWorks file, you have to enable CircuitWorks first. So you have to go through that process here. So you're going to have to enable under add-ins. There we go. I get caught up. Under add-ins or under tools and add-ins, you come and select CircuitWorks. You can enable or disable startup. This is where to do that. So like for this one, for instance, 3D Experience Marketplace it's not like this is a cute feature, doesn't matter for real life. So you don't really need that. Couple other things that you will actually need to take advantage of are going to be occasionally simulation. We don't use motion anymore. You really don't need those. And CircuitWorks is not one that's part of the CSWA exam. So this is a little bit less prominent. This is very much more for the EE students. But you want to make sure that's enabled as an add-in and hit OK. Then you should have a CircuitWorks tab show up after it's actually installed. So this is going to be a thing, and you can actually then go to open an ECAD file. So the E&M, so I remembered right. I just want the record to show that I remembered correctly. Their example 2 E&M, this opens in SolidWorks itself. There's two different ways that you can open that E&M file. You can open it in SolidWorks. You can open it in CircuitWorks. CircuitWorks is a separate physical window. So they have the boards. They have a couple of these things. I'll open up the cell phone in this one so that you can also see what that looks like. So this allows you to highlight specific components. I'm going to close out of this one just so that we don't have too much stuff going on. So SolidWorks, CircuitWorks. SolidWorks is just a drawing package. That's all it is. This is showing you some of the different components. When you highlight them, they highlight different parts of the assemblies. You can go in and make edits and changes to some of those, but this helps you see the actual physical layout of some of the components for the cell phone. Like this is the display down here. So the LCD, there's some other ones that are going to be fairly recognizable. So this one would be one of the main processors, for instance. There's other components in there too. So some are meant to be fuses. Some are meant to be other components. So like these, for instance, would be your volume switches. These guys would be volume switches. This guy would be your speaker component. There's another one, I thought on this side, that was the power switch, but I don't see it at the moment. Oh no, right here at the top, power switch. So power switch, volume switches, some of those things. So there's a few components. This tutorial is going to walk you through some of the details when you go to actually import it, and see what's going on. So almost all of this tutorial is physically done within SircuitWorks rather than within SolidWorks. And that's why you won't see all these same components. You won't see some of these buttons. So when you highlight it in here, it'll bring it to your attention. There's a couple more. So this kind of icon, I don't think this shows up. Yeah, it doesn't show up in the SolidWorks part tree. It actually shows up in the SircuitWorks part tree. So a lot of this stuff is all done within SircuitWorks itself. Each of these has a name, identifier. So speaker S330 for switch, 331, 332 are on the back side, which of course you can't see. You can only drag this around. They also have what's referred to as a keep out area. Yeah. So this keep out area means it has to have a minimum of 10 millimeters clearance in this keep out area. So a lot of different things that are present here in SolidWorks. You can show them as non-plated holes and plated holes. So you can highlight, here's all the non-plated holes. So those would be where your hardware goes through, screws, or other hardware for different reasons. Plated holes for mounting components. All those sorts of things are all present there. So you can do different filtering. You can go back to just the outlines. You can look at some of the different layers. In this case, really only has one layer to it, but there can be multiple layers. And then you can go back to highlighting the components and seeing which ones are which. And it will, so like this one is an antenna component X200. So each of these, you have a couple different things that you change the properties on, and you filter a couple things. So it's just kind of walking you through how to use the SircuitWorks interface. But every time it's going to hide that SircuitWorks window every time you switch back to the tutorial. It's frustrating. It just is what it is. But you can actually manipulate these components in their sizes and dimensions, place components. There's a lot of things you can do. So you can change properties. There's a lot of things that you can work in with SircuitWorks. It's clunky. It's not super great, but once you're done with all of this, you'll notice this build model doesn't exist here, but it does exist here at the end. So you can build the model, and what it will do is it will recreate once you're done. We have to close the SolidWorks document first. So in this case, got to close this one. So I have to say, oh, okay, yes, I understand. So we have to close that assembly. Don't save. We didn't make changes. So now we go back to CircuitWorks, and you will build those. Close all open SolidWorks documents. Right. So this one, even though it's a blank document, this is some of the little annoying stuff that will cause questions later if I don't walk through some of it with you guys because reasons. All right, so all the other stuff is there. Now we can build the model. Zero height components, 500 was 101, zero height components, which will inherit parts. That's fine for now because what we're trying to do is do this. Yeah, overwrite it just so that you guys can see what actually gets built. Don't show this again. Yes, to all. So it's going to recreate. It's going to recreate a few of these. So what it's literally doing, if I can get it to show it to you or not, but what it's literally doing is going through and it's creating from the instruction set each individual component so that it can then build the finished circuit with instructions, including materials and all sorts of things. So you are going to be creating the circuit for the four-wheel drive car. You're not going to be creating this. You're not going to be recreating this cell phone circuit from scratch. You are going to be following along with the tutorial and applying all of the steps and components. But as you can see, this particular process working with SolidWorks, this takes time. There's no amount of fast computer that makes this particular process go faster. It's single core, sequential, nothing you can do about it. So, but it's trying to get you exposed to the idea of packaging for contents on an actual circuit board and what that layout would look like so that the double E's can start learning how to start building their own housings for electronics and things like that in SolidWorks. That way we don't get to senior year and double E's have no idea how to build a housing. They just buy a bunch of rectangular boxes and throw stuff in there. We want them to be able to build custom housings for enclosures of things and build them into the design as part of it intentionally instead of just floating downstream and hoping everything goes great. Because rectangular boxes are great, but they're really hard to mount and they're not very aesthetic for things that you're going to be doing for your presentations for capstone and things like that. So as frustrating as this class is, this particular class actually teaches you the things that you need to know to do actual engineering, perhaps even to a greater degree than all of the hand calculations and math problems. Because a lot of your time is going to be spent doing work more like this, less like your boss hands you a bunch of problems and says, I need you to solve numbers 70 through 76 in the next 5 minutes before our meeting. Like that's not engineering. Sorry. They're going to say, I need you to design this thing. I need a prototype on my desk and I need it in a matter of minutes, not hours. So takes a few minutes to actually compile and finish Now it creates the assembly. That particular part is, I think, a multi-threaded operation. So process is complete. Now I'm looking to see, can I minimize this? There we go. All right. So finished project. You can see the rendered keep away area or keep out area, because there's a particular zone that has to be cleared. So then you can see the actual detail of the components. So they're not just rectangles anymore. So these are various resistors and surface mount dies, fuses, all sorts of different kinds of components to represent different surface mounts, as well as memory, processors, etc. All of those sorts of things. Front and back are all represented. This one I think is the reset switch. Can't remember offhand. No, that might be a external coax connection for diagnostic. I can't remember. Anyway, battery down here at the bottom, I think is what that one was supposed to be. It's been a little while since I've looked at this, but anyway, that gives you an idea for the actual rendered component. So cool, but it's definitely got some things that it's definitely kind of a challenging piece to put together. So that gives you some insights into the mechanics of how Solidworks works. You can import models equally. So that's one of the things that they want you to do with the assignment. And I'll go back in and double check that the instructions are improved. I think Dr. K said he had improved that particular assignment, specifically where we're building this circuit. They want you to build the physical circuit and then import it into SolidWorks, or import it into CircuitWorks, and then re-export it as a built model, is kind of the short version of what that is. So that's for later on. So I'm not going to save any changes to these. I'm going to close these out because they're in the way of what we're actually trying to get done today. But that'll give you an idea of where the tutorial is, where some of those other components are, etc. There's an awful lot that goes into it. You won't need audio, but I will need to bring up a couple things regarding the four-wheel drive cars so that you can see what these are, what is involved. This in my build, and no, those are not sped up. Those are actual full speed, not played at 2x or anything like that. So there are a lot of examples of these chassis, of different setups. There's people that do motor rewinds. Here's an example of some experiments that people do, trying to look at gearing and things of that nature. So this is an unloaded transmission. Purple gear is what you're going to be working with for the most part. We do have a couple gears that are this size. This is trying to go for like a super high RPM arrangement. It's possible, but it's tricky. We won't have a track that's anywhere near this complex. And a lot of our cars are not going to reach anywhere near those speeds. These are cars that have been optimized and had everything standard. In Japan, this is deadly serious competition. Like, I'm 100% sure people have been murdered in the streets over this, which sounds ridiculous to you, but the Japanese take this very seriously. So I think this one's an example of another chassis type. All of these are built to a particular spec. They're all built to within certain boundaries, and so that is attached in the document for this assignment. You see some chassis components. Ours are not going to be nice, handy kits like that. They're going to be custom built by you, custom 3D printed. So this is a big part of what we're doing in the coming weeks. So there's a motor. So you guys are going to be given a motor, wheels, tires, etc. I custom printed wheels and tires for mine, mostly because I just wanted to see if I could, if they would work, etc. They do, but there's no actual benefit. So there's lots of different chassis designs, lots of different classes, categories, lots of different gearing and setups. So this, ours don't have any kind of crazy inclines like this. So play sad dying samurai music. The car flips over and goes backwards. Oh no! Oh no! And he almost can't catch it because it's going so fast. Really sad because now he's brought great dishonor to his family. I just don't think you guys understand how deeply impactful this particular sport is. So it's really, really, really huge in Japan. A lot of different setup options. Everybody has rollers. Some of them have weights and other things. Some of the videos are done to totally non-matching music that wants to be rap or something. I don't know. Remixes. The point is, there's a lot of different variations. Some chassis types is actually really useful for the purpose of depiction. This chassis type turns out to be really useful. The exception is what you may want to think about in terms of design work for your chassis is taking more or less this idea, but shifting it off to one side. So I had a chassis type like this. I don't think I've got that one anymore, but I do have this one. What you want to focus on is trying to get the motor and drive gears and things maybe off to one side. There's also other types of arrangements where they do kind of a drive shaft between the front and the back with gears secured onto the shaft. There's a lot of different design options. So there's some people that put the motor in the front or the back and do a drive shaft across. This we don't have a lot of these kinds of tabs for making electrical contact to drive the motors. So those are cute and handy, but not helpful. So there's a bunch of different crazy options and examples. So if they go too fast, they can get air, but that's why you have to have those sorts of components. You have to consider all the different design parameters. There's a lot to building these. There's small scale models that people have made. There's making them from cardboard. Sure, why not? Like I said, really, really, really deadly serious business, the way that a lot of this works. So there's some chassis types you can get inspiration from out there. You're going to be given components like drive shafts, wheels, tires. All of those are going to be basically the same. So there's some pretty cool things that you guys can do. You're going to be given a spec motor. So there's a lot of different ways that you can approach this from the design perspective. But you will find in this, so the control board design, that's the assignment that I was talking about, the control board design. I'm going to get you guys set up in your CLC groups today. The CLC design and the circuit board, that's what this one is doing. So let me pause for a second and get this opened up so that you guys can see this. Okay, so good. He gave you a bunch of the components. So like I said, a couple of these things have been improved. So as far as documents, this is what's attached. So you actually have a control board file that's a starter. That's going to save you guys tremendous headache versus what we had going on last fall. That was not great. But you guys have some header components, and I think the board design itself has been simplified. So let me see. Yeah, because he's actually got yeah, so he's actually got the switch document. Great. I made a version of that drawing, so you guys are welcome to use the one that's attached. We didn't have any of those originally, but I think I included. Maybe I don't have that switch. Okay. So yeah, that's a really good one to have on hand. So then the control board itself, that will be immensely helpful because I think he converted over from the Eagle file, which is what the EMN extension indicates. So this is where you're going to be recreating that. So you're going to set up the process. So he's already done the work in Eagle to set that up and lay it out, and then put together the CAD model, then drop it into Circuitworks as an IDF file. So it's a bunch of steps, but it's actually fairly straightforward. The actual Circuitworks tutorial is the one that I showed you today. So that's what's coming up there. The mini 4-wheel drive, this has the actual attachment. So here's the list of things that you're going to be given. You're going to be given a motor, gears, control board, battery holder, axle, wheels, batteries, cables to attach stuff, some hardware, and then a print sheet. What that means is you're going to be taking all of your parts. You're going to be printing the chassis. We need to do a lot of design revision and assembly in SolidWorks first before we go to assemble them in real life, because you won't have the opportunity to do a gazillion different prints. So even if you're just printing one single component, that counts as a print. So your total number of prints is 3. So that's 3 print beds that can be used, and that's final. So there's a lot of things that you can do there. There's a lot of things that you really can't do there. Anyway, there's some options. So things that you'll want to keep in mind. This is the spec sheet, or this is the print sheet that also covers the kit components. So there's a spec width, length, height, Ground clearance, you want to make sure you've got at least 1 millimeter. Really, really important to have probably actually a couple millimeters total ground clearance by the time you're done, because reasons. Has to have 4-wheel drive, so there's points associated with all of this. The weight, 90 grams, we're not as particular about. Rollers, you can have as many as you want. They are really important because reasons. Got to have rollers to be able to help the car change directions. The 4-wheel drive cars with no rollers can't really change directions, creates a lot of problems for you guys. So you're going to fill out your print credits, and this is designed to be a whole sheet. So each kit should have 1 motor, 1 control board, 1 battery pack, 4 wheels, 2 hex axles, some round axles, 2 of the small purple spur gears, 4 of these blue gears. So the blue are 2 different tooth patterns. So they're the 36 and 12, I believe is the blue. 4 of the blue spur gears. So the ones that, that's the 4 spur gears, the blue ones. The 2 yellow crown gears so that you can change direction 90 degrees with the rotation. And then 2 yellow nut spur gears, which are ones that anchor to the hex axles. So that's the key things to understand there. And an Allen wrench for those. So you are going to have points assessed for the actual 3D print part of it, how well your team is working together, all of those things. So you want to make sure that you're thinking through how to actually get things printed off in a way that makes sense. So there's a bunch of particulars there. The instructions have been greatly improved for that. And then, so we've got the 4-wheel drive check-in that we're working on. So these we've added in as mile markers. And these are going to be really important in keeping you guys moving along. So we need you to fill these out with more details about images of part renderings, assembly renderings, what you guys are working on, where you're making progress, what your manufacturability is going to look like for 3D printing. So there's a ton to this. This is what's going to come up. So you guys are going to start doing that this week, and that's going to be the remainder of today's time, is to start making all of that happen. So I've given you, in lieu of some of the direct measurements, that's why I've given you some of these other files. So I'm really glad you guys have those new ones. That's really helpful. So that's why I've given you some of these files. It's not the circuit components, but in the gearbox. So I've given you some more detailed drawings about the actual gear. So this is an example of the crown gear. This is an example of the blue spur gear. So 36 and 12. What I call the lock gear. So it's a lock nut spur gear. Some details there. And I give you in each of them what the pattern looks like. And then as a reference point, in order to understand the gear lash, you can recreate part of this frame if you want to. This is the outside frame, and I'll do a quick assembly with a couple components for you to show you what this looks like. This is the interior side of the frame. So frame 1 and frame 2, there's 2 of frame 1 on the outsides of frame 2. I'll put this together so that you have some kind of a sense of what all of this is. in terms of geometry. Let me pull that up in SolidWorks so that you guys can see. Let's see. So I'm going to pull together frame 2, frame 2. All right. So the center section of this particular one is designed to be a dual motor frame. So you'll see what that looks like in just a second. I'm going to make an assembly from this. And this will give the opportunity, let's see. Frame 2, set it up here. We're going to grab some more components, frame 1. And I think I did a mirror of frame 1. So, yeah. I think I did a mirror of frame 1 as frame 3, if I remember right. I'm just going to use a couple of these. So I'm going to use a 30. I'm going to use the 36 because the 36, so this is a spur gear. So I need both a ring gear and a spur gear, and I need a lock gear and a lock nut. So this is an example of what you guys are going to be putting together as components. So there's 1, 2, 3, 4. Okay. So each of these components, and then I thought I also had like a hex shaft, but maybe I don't. Yeah, 23 millimeter shaft. So insert insert should be able to insert from an STL. Maybe I didn't save it as a SolidWorks part. Yeah, it doesn't look like it. So I'm gonna import those real quick. Change back over to the frame window, but I've got to step out of that first. All right. So I'm going to open a couple more components. So 23 millimeter shaft 2. So there's a small one. This one I think is a longer one. No, maybe they're the same. Okay. Save as a part, 23 millimeter shaft. I think there's one other STL that I'm going to need. Here we go. 50 millimeter shaft. So this one has a hex section, and that's what I was looking for. So I'm going to save that as SolidWorks part. Now go back to my component long story of why those weren't originally included. All right, that'll be good enough for what I'm trying to do. Okay, so what we're doing here is we are lining up the components. So um, easiest way to understand what's going on is to get these uh, set up to be concentric. So we've got a bunch of mates to add in. What we're going to look for is um, concentric. How did I do it last time? I think maybe what I did was actually did, instead of concentric, I started with parallel. And I think I picked something like this plane and this plane as parallel. I might have actually, yeah, I did parallel. So that maintains one part of the orientation. These come inside slightly because these aren't, oh yeah, okay, these are flat surfaces. So this one and this one are going to be parallel, and we flip orientation. So that is correct. This now I can flip in orientation by saying this face is going to be coincident with it's going to be coincident with this face. Flip orientation. All right. This I now need to rotate. Easiest way to do that is undo those two parallels and say, let's do this point and that one does go back. Actually, it's going to be easier to do clear selections. It's going to be easier to grab this point and this point and make them coincident. So I'm going to clear these selections because that point and this point need to be coincident, but they need to be coincident in an anti-parallel way. So this, what I'm going to end up doing is I'm going to end up doing a rotation to make this, because this is imported from an STL file. You guys aren't going to have to do anywhere near the same degree of things as I will in order to make this work. This one, I actually need to rotate it about this axis. Let's see. Free drag, I need to make sure that the mates are cleared, because this coincident is creating problems, because I need to change the orientation of this exactly 180 degrees this way. So this now, there we go, a lot closer there. Now I can freely drag that component. Okay. So this is now going to be a whole lot easier to make parallel. So now I can start including the mates. You won't have the same difficulties that I will for a lot of reasons. Face 1 and face 2 need to be parallel. Oh, nope, not that one. That was supposed to be that face and this face as parallel. Check. And then one more we're going to need to do. So I'm going to do another free drag of the component. Because it'll be a whole lot easier to understand what this gearbox is doing this way. So I'm going to set up this plane parallel to this plane. Okay, and then I'm going to do a coincident between, actually, I need to rotate this 180 degrees to get the correct geometry. Yeah, let's do that. So this actually goes on this side because reasons. So I've got to flip this one. Kind of get out of the free rotation and flip this orientation, because that is, nope, flip that orientation because that's correct. It'd be really hard to envision without that. So let me see if I can flip this one also, because it needs to go truly the opposite direction. It needs to be anti-alignment, which is good, because now what that means is I can do a free drag and get it positioned to where it will have a little easier time getting aligned. Okay, so yeah, this is an interesting one. I'm going to get these 2 points coincident because that should give me, so this edge and this edge coincident. Okay, and actually, nope. Undo. So that edge is too far this way. So this front edge and this front edge are going to be better. Yeah, let's do that. So this front edge and this front edge need to be coincident, along with, there we go, and this face and this face on the inside to be coincident. Okay, there we go. I'm not interested in the errors that that's going to cause right now. Long story as to why. The motor goes here on this side. So this will give you a pretty good reference point for how far the depth of the motor needs to be. The axles go through the center here, and that will help to arrange a couple things. So that one we can probably even delete at this point. And that eliminates some of our headaches. Now you can see kind of where the gearbox components go into place. So the spur gear, for instance, once you've drawn it, you won't have all of the extra lines and features from the STL. Really, really helpful because you won't have some of the same challenges. So the crown gear is actually going to go here and interface with the small spur gear coming off the motor. So I'm going to put that into place so you guys can kind of visualize what's going on. So this plane needs to be basically coincident with this plane here. That way we can then take our free component. What I'm going to do is I'm going to fix frame 1 so that it's no longer moving. So frame 1 and frame 2 are fixed. Now I'm going to do a little bit of quick free drag for this component. So pretty well lined up there. Okay, that's going to be pretty close. I set the size, there we go. So these are now concentric. Okay, good enough. So there is the gear. You want to make sure that you're not actually any lower than that surface because you're going to have bind issues. You notice it's just barely going to clear this idler shaft. Actually, this is going to be on an idler shaft. So this guy is, I'm going to move this guy. It's going to be, um, that's going to be concentric to this. So I'm going to see. Getting a component like this to actually be concentric is going to be really, really tough. So what I'm going to do is set up a mate for not that vertex, but that one. I'm going to set up a mate between that vertex and this one. Um, then I'm going to set up one more where I've got something like this vertex and this one or something like that. Okay, it's not going to allow that one. What I can do is I can do a free swing of this one and get it pretty close. So move component, that one. Okay. So it's closer. That may be almost. Let's see if I can get another point comparison. So this will be pretty close. Something like this. And I may not be able to get it to rotate cleanly. But maybe I can just change the view and get pretty close. Okay. So I'm going to drop out of that, move component. Okay. Something like that is getting us pretty close. Um, I wonder if I can get a parallel instead. That might work better. All right. That should be, that's sufficient. Okay. So that's showing more or less alignment of the center shaft. I'm gonna have to do the same thing to this one. Okay. Back to free drag. Okay. What this is gonna do is give the at least the sense of, let me see if I can get a little better rotation there. Uh, because it won't give any kind of meaningful tangency to this. So I'll see if I can get it to cooperate. But even if, honestly, maybe if I even did a parallel for a face, that might work. So if I did a parallel of a face in this, okay, that'll do pretty well in terms of alignment. And then I just relocate the component. Okay, yeah, that might work better for this. So you'll have the opportunity to work a little bit more seamlessly on your projects. You won't have the same STL issues that we're having here. You can obviously see some clearance issues there, but that's okay. This guy, wow, that's really awful. So this would rotate the center here. I'm gonna have to probably eliminate this one. So I'll rotate that just slightly. Okay, that looks better, sort of. All right. That gets us pretty close, good enough. Okay. So that gives you a pretty reasonable idea, I think, of what this will look like. It's not going to be total perfection, but this will allow us, for the purposes of this, to show something about gear lash. That's a really important component of this. So as you get these centered, I am going to do a parallel between, let's do that face and this one. Okay. Then I can go back to my free drag and get it pretty close. So you'll be able to do nice, clean, concentric operations, whereas I won't be able to do those to the same degree, but you'll see here, for instance, that gear can't interface here because there's zero clearance. And if you bring it up, there's going to be not enough teeth to actually mesh. So what you actually have to do is do an anti-parallel, do a flip, and bring this up so that if you wanted to run it, you have to run it like this, where you have clearance underneath the gear, you have mesh in those teeth, and this will get you, once with everything actually properly square, and not having some of the alignment issues, concentric, you'll have good meshing and you won't have the same kind of clearance and gear lash issues. But you'll note the cutouts are very specific here so that you don't have stuff actually catching on those gears and binding. So but this will give you some ideas of how do I put together the components that I need. Because now, for instance, you might have additionally this lock gear. So you might use this gear, you might not use this gear. Maybe you say, I don't want to use that one. I actually want to use this one. And you say, okay, I want another one of these that is parallel to this face here. And it's got to be a face to face. Okay. So this one, I can already tell we're going to need anti-parallel. So here, okay, bring this up a little bit. Okay, so for instance, you can do the lock gear here, and it'll drive and mesh rather nicely with this gear, leaving room for the crown gear. But you've got a lot of tight clearance here, but you'll have engagement with the spur gear here, rotates this gear on an idler. Then you have the lock nut that goes on here, locks this to the shaft, and now this becomes your drive axle. And instead of the gear out here, you'd have your wheel out here somewhere. So this gives you a lot of detail about spacing, getting gear lash correct, all those things. If you follow the drawing very precisely, you can use this as a starting point for your chassis and build up around it, using and factoring in, of course, these other components. The height, width, length, ground clearance issues, because you really want to be able to keep these in mind. And then another rule of thumb, you can 3D print your rollers, but you want to keep this in mind as well. The minimum that you want to use in terms of diameter, a lot of students set up posts and they make them, 1 millimeter in. They make a 1 millimeter shaft that's supposed to somehow hold on to the roller and then keep it going around the track. Not only will that not have a high degree of success in terms of printing accurately, that millimeter shaft has no strength and rigidity. You need to have a minimum, absolute minimum of about 4 millimeters thickness on that post in order for it to have a chance of surviving both the printing and construction processes, let alone the actual race itself. So these are just 3D printed rollers. They can be bigger, they can be smaller. I like bigger ones because that means I can keep a low profile in terms of the chassis. So if you think about it coming up against a wall, one of the things you have to think about is the geometry, because it's not going to run straight into a wall, right? But it's going to run into a curve at a pretty sharp angle. What you don't want is you don't want the tires hitting, use maybe a 60-degree angle or something as a reference point. You do not want the tire interacting as the car turns. You do not want that tire to be able to interact with the wall at all. At no point can the wall grab onto that tire, because if you do, you're going to lose tons and tons of speed fast. So you don't want to do that. You want to use something like this where that radius, no matter which direction it's going, the tire cannot touch the wall no matter how hard it tries. Even if it's flexing, it cannot touch the wall. So you might have to print a few different size rollers. They can be helpful in the back. I've generally found that for these printed cars, the back rollers really aren't helpful, but you also want to try and keep the profile of the body itself narrow relative to the width of the actual track itself. Because we've had some students that are like, wow, I can make it, 105 millimeters wide. So they made a 100 millimeter wide body and they made it 165 millimeters long. So they basically just put a brick in there, and then they expected that brick to be able to turn smoothly. Doesn't happen. So you want to be careful about your design choices in regards of being able to actually make the turn, because the car doesn't have the ability to steer, it only has the ability to go. So the better you can, especially with bigger rollers, it's a whole lot easier and less effort for it to turn. And there's even some ways that you can design in the rollers to be printed as one part. If you guys are interested in seeing how that's done, I'm happy to give you a demo. Let's have a vote in the chat. What do you think? The rollers don't have to be mounted to the rear. They can kind of help keep the cart straight so that it's not just trying to, track down the track sideways or something if your axles are hugely misaligned. So it can help. My experience has been the difference the rear rollers make compared to the front ones is almost nothing. So it'll help kind of keep the car square in the track. But honestly, I've not found them to be necessary for this particular assignment. You can get a car around just as fast with front rollers only. And so that was what I was trying to do with this one, was absolute top gear ratio. I'll see if it'll actually cooperate long enough to let you guys hear what the RPM rate sounds like. You'll also hear how much the motor struggles to kind of get it up and spinning to overcome that inertia. So I'll see if it'll pick it up, maybe if I'm talking initially. So it reaches it, especially this particular motor, because of the way it's geared, they just don't have enough torque to overcome that initial inertia. So as soon as it starts rolling, it ramps up, because this particular motor is supposed to be capable of about 20,000 RPM, which is a lot. It's substantial. 20,000 RPM at this gear ratio should be able to allow this to reach top speed. I forget what the actual effective speed should be, but it should reach a scaled speed of something well in excess of like a couple 100 miles an hour. So it was designed to be very, 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 very fast top end. But these motors just don't have enough torque. So I would need to have 4 batteries and 2 of those motors minimum. And even then, I don't know if that would be enough to actually drive it forward. So there's tons and tons and tons and tons of design considerations for this. So single print rollers, I can show you guys real quick what that looks like. So let me go back to another drawing, and then I'll screen share while it's thinking about it. So print in place rollers are possible. The way that you have to do it is like this. So for this, I'll add a sketch. We'll just do top plane, keep things simple. So we'll say this is our chassis, and I'll say for the sake of argumentation, this is our front pad. This really needs to be a minimum. I like to do really about 6 millimeters or so as the base for a minimum. You could go with 7, so you could do something like 3.5. And then what you can do is, again, I guess on this same plane, before we get too excited, you can do a wide roller, so something like 1 inch or 3/4 inch radius So it might even be a 0.875 inch radius, something like that. Good size roller. Doesn't have to be super huge. I've just found somewhere in that range of like an inch, inch and a half is okay. And then a top roller piece, because you're going to need some kind of retaining cap on it. And what you can do is yeah, you want to make it something like 6.5 millimeter. All right. So now what we can do is we extrude. So we take maybe this is our chassis base. We do something like 4 millimeter. There's some other things that you guys can do to cut way back on print time. One of those, for instance, is you can do something like 3 millimeter. Another just kind of quick tip while I'm thinking about it, on this top plate. So if you did something like this, for instance, and you did this, extruded both of those, another 3 millimeters, right? Now you actually have a chassis that's very rigid. It's not flexing and bending a whole lot, but you can take this kind of ladder bar idea. It could even be tapered or rounded to save further material. Like there's tons and tons of options. But we're going to do another extrusion based on this first sketch. So we're going to extrude this base. We're going to bring it up. It's usually got to go up 1.5 inches, closer to 2 inches. Minimum really is probably going to be about 40 millimeters. Then on top of that, we're actually going to extrude a part here. We're going to do an extrude, but we're going to do it this way, where you take this whole base, as well as this and this inner region, and pretty much what you do, including this one, nope, not that one, but this one. So this circle region, you extrude from this surface, and you have to be kind of a little bit careful how you do this. I'm going to go ahead and extrude this interior region as well. But we're actually going to be I'm going to dip back down here and see. So we need this piece, this piece, this piece, this piece, this piece. So all of those regions, you really only need to go up about 4 millimeters to get it to be sufficiently thick. But you do need to make sure you're also incorporating this region here. So you've got to incorporate this region. No, I want that region and this region, but not that one. And I want to extrude it from this face. So This one, because of this weird cutoff, creates an issue. Okay, want that region. Nope. Deselect that region. I'm going to change that base sketch real quick so that I can get a little more clear. This particular one has got to go smaller to avoid the clipping issue that I'm having. Long story as to why. So this boss extrude. Clear selections. So this one, this one, this one, this one now is okay. Should be okay. Why are you causing rebuild errors? Because of this zero geometry going on. Let me make one more change. No, break the tangency, break all the things. There we go. Okay. All right. Good enough. So I'm going to step out and rebuild the part. Now I'm going to go back and do the base extrusion from sketch one. Whenever there's conflicts within the geometry like that, it's really hugely problematic. But I want to take all of those regions and this center section. I want to take all of those and this up 4 millimeters from the face, which is this one. And then what we're going to do is we're going to do an extrude cut in the center. Then we're going to do some revolves we can do a revolve cut, but it's easiest to do an extrude cut here. What it's going to be is it's actually going to be a tapering cut. So from sketch one, we're going to actually do an extrude cut from the surface, from this surface, flip direction, and then we're going to do a taper, but we're going to draft outward by something small, like 5 degrees or so. Okay, so now we have this sitting on the top. You kind of want to offset these by a little bit. And so actually a better way to do this, let me change how I'm doing this cut. So we're going to draft inward. We're going to flip direction. We're going to go from this surface, actually. We're going to draft inward so that you only have a small ribbon of material that overlaps. What this will do is this creates the circumstance for a roller to be able to be broken free at the top without kind of compromising the rest of the material. So it's a little bit tricky to pull off, but very doable. I'm going to do another extrude of sketch one. I'm going to do this base circle again from the top. I'm going to do from the top surface. We're going to do downward. So we're going to flip direction. And we're going to draft inward by a slightly steeper angle, and we're actually going to do an offset instead. 45 degree minus 45 offset. Oh, no. For an offset of 45 millimeters. So what that does is and increase this to 5 millimeters. So what that does, we can even increase it by a couple more. 46 and 6 millimeters. What this does is creates a gap in the part, so that those two, depending on the resolution of the printer, shouldn't really be completely fused together, or shouldn't be completely fused. And then you extrude the larger circle and the inner circle from this offset with 2 millimeters. So what this does is this creates kind of a cap so that it can't ride up. And you might need to increase. You can do it's easier not to do tapered holes. It's easier to do an inner concentric circle for this middle part. And then this can work as a print in place roller. If this fails, then you just have the machine shop help you drill a hole, put a screw through, and you're fine. So if the print in place fails, it's kind of no big deal. And that way you have just a little bit of overlap in the material. So if I switch to wireframe, you have just a little bit of overlap in the material, not a lot. You want to have, like one line of print material, so 0.1, 0.15 millimeter between these two. But that'll give you a print in place roller design. So this started out as a print in place roller design, and then worked a little bit easier. You can also round them, which I highly recommend. So doing a fillet along both edges of 1 millimeter. You can do, you can get away with 2 on these. And then same kind of deal with these. You can do a fillet of 1 millimeter. And then you have a fairly clean cap. You can also do a fillet on that surface as well. And that one you can do something more like 2 millimeter. And that will help to reduce. You can do it asymmetric even. 2 and 4 or something like that. That'll give you some additional clearance. So lots of ways that you can do it to make it so that it should kind of basically, when you get the print, you carefully hold the base and you twist this top piece and it'll shear off, and then have a twist print in place roller. Downside is that can add a lot to print time. So because they have to do support material and things, so it's not as fast and efficient. But if you're really solid on your chassis design, you can really get a lot of mileage out of something like that. So anyway, that'll give you an idea for how to do some roller designs, and a couple chassis ideas, you're going to want to do you're going to want to kind of carefully space out your axles from each other and spend a lot of time really kind of building out at least part of that assembly, so that you can get a good sense of, okay, how far do these have to be apart. That way, when I print them, they're going to be pretty close to exact, and that way I'm not going to have issues where I misaligned the holes and they're too far apart, the gears don't engage and they strip out too little, things like that. There's options. So this kind of a housing design for the motor itself can really help as well. You want to make sure that you're getting these particular dimensions really exact, because that's going to help tremendously. And then, yeah, you can effectively take something like half this chassis and put it on one end, and the other side of the motor is kind of like a mirror, where you can see they snap in. Then you'll be able to see the back of the motor is slightly different than the front of the motor, but you can get some pretty good ideas what's going on there, for a few of the components in terms of spacing and all of that. So there's a lot that you can accomplish. Okay, so that's kind of quick lesson time on four-wheel drive cars and the 3D printing chassis. Any questions on this? Because I think that's where a lot of things come into focus. I think there are some 3D printed designs out there. So not some of these RC car ones, but there is a design here. You guys, if you want to send me a message in Halo, you can send requests for teams. So that's a mostly 3D printed example. He's got a really nice switch going on. He's got really good batteries and stuff going on in there. But that's a pretty cool concept that he's got going on there. So you can take inspiration from other stuff out there, snap covers, all sorts of things. Really, really great ideas. You will be printing them on the school printers, so you guys will be getting files put together, and the lab staff will be helping to get those off. Let's see. They do have a couple more examples here. No, I don't see a lot more in the 3D printed realm. This one is a RC conversion of a 3D printed chassis, but maybe it'll give you some good ideas. Interesting. So they took some design principles, did some modifications. This is that drive shaft model idea that I was talking about, where you put a dual drive motor at the front or the back, put the batteries somewhere in the center, then have a drive shaft running up one side or the other. So definitely a thing that you can do. So he set up bearings and all kinds of fancy stuff in there. Wow. Really rough prints there, dude. Yeah, that'll work. So he's using a couple cast parts and some 3D printed It looks like he had resin printed gears. I think they were starting to resin print gears for you guys at last I remember. Um, there were a couple more things. Um, no, he's got grease goobered all over those. That's what's going on. So, motor in the back, uh, spur gear on the motor, drive and driven gear, and then this guy is a crown gear. Oh no, it's the pink. Yeah, the pink gears are driving front and back. Um, so you'll be given the tires, battery box, motor, a bunch of other stuff. You'll be able to get some real physical measurements from those shortly. They should be in the 139 room already. I'll coordinate with lab staff to make sure you've got those parts available. Okay. Other questions about these four-wheel drive cars? Since this is kind of the majority of what we're going to be doing for the rest of the semester until those are closed, because we have the actual final race. We have the actual final race in week 15 for this class. Because you guys need every day to build. So typically week 14, which is 3 weeks away, we will have our final build. Oh man, he's doing steering knuckles. Wild. Okay, that's clever design, actually, legitimately. Well done, sir. Well done. Still four-wheel drive. Yeah, very cool. Bar and everything. So the materials you're going to be getting, I'm going to make sure the kits are in the classes. They'll be assigned per team, so I'll let them know how many teams I've got. I'm going to do about 4 to 5 in total. So that way you guys have plenty of detail. But this guy going over the top really helps to illustrate the whole. Oh, steering servo at the back. Wild. Yeah, this helps to illustrate the whole, like, yeah, you're mostly limited by your own creativity, not really by the selection of materials available to you. It's really down to creativity more so than anything else. So you will get the materials. I'll try and make sure. I know they've got some already in the room that you guys can at least take measurements from. You just can't take one of the kits from the other classes or anything like that. So that'll be a starting point. Um, yeah, we've got. I'll be emailing them a little bit probably later tonight about some details. So you'll get another announcement with some more information about this shortly. Um, yeah, it's using some Spectrum parts, good stuff. Um, yeah, like I said, this stuff is taken deadly serious in Japan. Like, I'm 100% sure people have been murdered over these four-wheel drive cars. Like uh, some teenagers say this is what keeps them out of trouble. So they do have speedometers. These guys will actually reach, in some cases, 40 kilometers. Maybe that's what it was. It was actually supposed to reach something in excess of 100 kilometers per hour. So super fast if they are geared correctly to make use of the torque of the motor. In this case, I just had not quite enough torque for the kind of psycho RPM I was trying to achieve. So in experimenting, it can cost you a lot. But yeah, he's got a pretty effective little RC car there. That's legit. That's quick. All right. Any other questions? go ahead and stop the presentation there. I'll be looking for the recordings to see what we've actually got. There's a lot in terms of what we're trying to do. So I'm trying to make sure that you guys have as much information as possible. So teams, what I can have you guys do is I can have you guys message me if you want specific teams. So some of you were not particularly happy with the first round of teams, which is understandable. That happens pretty frequently. It's helpful to see who is there, who is participating, all of those sorts of things. So I'm a little bit flexible on that. It doesn't have to be. It doesn't have to be necessarily like you're sending in 18 different sets of recommendations or anything crazy like that. You just want to make sure that you're covering the bases, because there's going to be teams of about 4. Some teams will be 5, just to keep things able to be moving. That's the really hard part. So want to make sure that you guys have enough hands to keep stuff moving, but not like teams of 6 or anything crazy, so that nobody really gets to feel like they participated. All right. Other questions? All right, I don't see any. So I will try and get all caught up with messages. I've got a bunch of other projects that also need to happen. So there's going to be a lot. If you guys have some really awesome chassis designs or some things that you want to test out beforehand, I may be able to do 1 or 2 prototype prints here to see if they would even work. So we'll see. All right. I guess with that, hopefully you guys have a good rest of your week, and I will try and catch up with you in the messages.